Let's now look at how sound is represented in binary, and we could have done this before, but let's first talk about the difference between analog and digital data. So analog signals, waves, data, whatever, are constantly changing and we don't have defined ranges. So basically, they're naturally occurring signals like sound, like just light, pressure and so on. And they're often represented by waves because they're continuous. And we can't deal with analog signals, we have to deal with digital data. So this is where data forms discrete values, so they always fall within defined ranges and at set values within these ranges. So we need to basically, because the computer can only deal with digital data, we need to convert from analog, which is usually what an input and an output is, so there needs to be some conversion in this process. So in terms of how we do this for sound, this is generally done by taking a sample of the amplitude or height of a sound wave at regular time intervals, and then we assign a binary value to each reading. So sampling is recording a signal at regular intervals, and this is the key bit, regular intervals. So we've got a sound wave here, just a sine wave for the basic example. Obviously most sound does not look like this, and we at set time intervals, so here we've got a set time interval of 0.5 seconds, which is very unrealistic because it'd be an awful quality recording. And then we record the amplitude value at each position, and this amplitude value is in decimal here, but we'd convert it to binary, of course. A key term then is the sampling frequency, which is the number of samples obtained per second, and it's measured in hertz. Hertz as a unit is just per second, it's used all over the place to do frequency because frequency is per second. So here our sampling interval is 0.5 seconds, so we have 2 samples per second, the sampling frequency is 2 Hz. And the greater the sampling frequency, the higher this value is. The truer the digital signal is to the original, but the greater the file size. So there's always a disadvantage of increasing the quality of our digitized version. If we sample only 2 points, we get a very different wave to our original. 6 points is slightly better, and 10 points is better as well. So this is an increase in sampling frequency, although we don't know any times here, so we can't give an actual value. You might see the sentence kind of rewritten in terms of quality, and I personally try and avoid that because, at least to me, quality is more about our perception of the sound, whereas we can analyse our digitised sound wave versus the original analogue sound wave, but we can't really put a measure on the quality of the sound. Another definition you need to know is the sample size, and this is how many bits are available for each sample, and this is also known as the bit depth. And this is basically the same concept as the colour depth for images. So how many bits can we allocate for each sample? In this example, we've got the analog wave in red and our digitized wave in blue, and ignoring kind of the sampling frequency, this is much more about the y-axis as opposed to the x-axis being time. So this has a sample size of 3, and this leaves us with only 8 discrete levels of volume. So amplitude is loudness in sound waves, the height is loudness. So we only have 2 to the power 3 discrete levels of loudness. So clearly we have a low range of volumes here. If we increase the sample size, we'd get a much more realistic range of volumes. Another term you need to know is the bit rate, which is the number of bits used per second, and this comes from the sampling frequency multiplied by the sample size. So the base unit of bit rate is bits per second, and the other 2 units are hertz and just bits. So this is kind of like how much data needs to be stored per second, and this allows us to work out file sizes. So a high bit rate leads to more detailed audio or better quality audio, but you also need more storage because you're using more bits per second. You need more bits available in your memory to store this audio. Perhaps to explain bitrate a bit better, if we talk about the file size in general, so just in bits in general, this is the same as the sampling frequency times the sample size times time. So basically the file size equals the bit rate, which is these 2, times time. So the bit rate is just per second, is the data used per second, but obviously to create the full file size we need to work out how much data is being used per second, i.e. the bit rate, and then work out how long the actual file is, so how long the sound file is. So that's why we multiply them together. So bits per second is bits over second times second, so the s's cancel out, if that makes sense. And by the way, it's really important to realise, in case you get an exam question which asks you about, say, the sampling rate or the sampling resolution. So sampling frequency, same thing as sampling rate. Frequency and rate are basically the same thing. Sampling size is the same as a sampling resolution, so kind of a detail that each sample holds, and resolution is all about detail, as we looked at to do with images. So make sure you are aware that they're synonyms basically for the terms we've looked at.